Hi everyone. This is a short, not very professional video just to help you out to understand the idea of linear regression with calculus. So don't process what you see on the board here immediately. Let's just have a conversation. So you have endpoints in the plane, say x1 through xn. And this is a picture of some sample points. And you'd like to find a line that fits those points as best as possible. So fitting those points as best as possible means what? What's the criteria? What's the score? How do you tell one line is better from another? Well, one idea is to use the distance from your points to the line as a measurement of how far you are in total. One measurement is to take the residual. The residual is the distance from the point you have to the line you want to have. And you square that residual. I visualize that with a green square. And you'd like to create a line with the sum of these squares being as small as possible. You'd like to minimize the sum of the squares. And I'm using the summation notation here to save me from writing d1 squared plus d2 squared all the way up to dn squared. I suppress the index I equals 1 to n just because it's extra writing. What is this sum a function of? Well, the xij and yij are fixed. They're picked for you. The only thing that you control here is the slope and the intercept of this line. So this sum is a function of the slope and the intercept of that line. I called it S for sum. That's why this method of linear regression is often called the method of least squares. So you need to take the partial derivative of s with respect to m and with respect to b. And remember, partial differentiation, any differentiation is a process. I'm going to take the derivative with respect to m of this thing called the sum. That means I'm going to take the derivative with respect to m of each thing in the sum. And that means by the chain rule that I'll have 2 times di, 2 times each d, each residual, but multiplied by the partial derivative of di with respect to m because di is a function of m. So when I sort out all that fancy language, the partial derivative of di with respect to m is minus xi. Whether I say I or j or k here, I'm just referring to a specific point. So I have the summation of 2 di times minus xi, and written out, it would be in this form. Likewise, I do the partial derivative of s with respect to b, and you can work that out and check that I get this. So what does it mean for partial s, partial m to be 0? It means that this sum of di xi is 0. You can imagine dividing by the minus 2. To say this is equal to 0 is the same thing as dividing by minus 2 and calling that equal to 0. If you expand that out, write in what di means, you have this expression, equal to 0. And then you can break that into 3 separate summations. You're summing the whole. You're doing 3 summations here. And these 3 summations can be written like this. But the m and the b are constants. Constants in the summation can be pulled out. So really you have m times summation xi squared plus b times summation xi equals summation of xi yi. And that was one of the conditions that the problem asked you to meet. Now you could similarly study partial s, partial b equal to 0 and find out what that means. So what is your problem now? Your problem now is that you found out what it means for m and b to be a critical point, but you don't necessarily know that this critical point is what causes the minimization of the sum of the squares. So identify critical points, and now you have to proceed to the second derivative test. I'll let you give that a shot.